Now, this session will be delivered by Dr. Balakrishnan, and on behalf of Chandigarh University and all the students and faculty of Aerospace Engineering, we are grateful to have Dr. Arun Balakrishnan, Calibration Engineer, John Deere Power Systems, Waterloo, United States of America, with us today, who have accepted our invitation to convene this session. Now, Dr. Balakrishnan is currently working on diesel engine performance and emissions calibrations for a variety of John Deere applications such as tractors, wheel loaders, harvesters, excavators, and in compliance with final tier of 4 EPA emission regulations. He is involved in the calibration development of non-road engine applications through test cell work and model-based development. He received his BE in Aeronautical Engineering in the year 2010 from Tagore Engineering College, Chennai, and PhD in Aerospace Engineering 2017, specialized in combustion fuels and engines from the University of Oklahoma, USA. Since then, he has been working in the field of calibration development for various diesel engine platforms. So with this, I would like to request Dr. Arun Balakrishnan to take over this session and start with his webinar today. Thank you. Thank you, everyone.
Thank you for the introduction. I hope you can hear me clearly, right?
Yeah, yes, sir. Yes, sir. You are completely audible.
Okay. So this is the first time I'm using this Blackboard. So I'm trying to see how to share my screen.
Sir, I can just guide you a little bit.
Uh-huh.
In the participant column, you can see something in the participant. It will be written over 3738. If you could see in the down.
Okay.
Attendees. Sir, on that
Okay.
particular
Yep.
tab,
Got it. Yeah.
yeah. Share content, and from there you can go to the share application screen.
Okay. Just let me know if you see my screen.
Yeah, sure, sir. Yes, this is visible. Students, is it visible to you? You can just type it in the chat box. Okay. Yes, sir, it is visible. Sir, please go ahead.
Okay. Yep.
All right.
Okay. Good morning, everyone. My name is Arun Balakrishnan. As the introduction said, I did my Bachelor of Engineering in Aeronautical Engineering from Tagore Engineering College, Chennai. My undergrad mentor was Professor Dharmender Singh Chand. So he's very close to me, and he was one of the most influential person on me who inspired me to reach wherever I am right now. So he was our undergrad thesis advisor for our final year project. So he is the one who actually encouraged me uh, to take up this propulsion course, and from there I moved on and started gaining more interest on the combustion field. So I owe a lot to Professor Singh. So let me get into the topic. So today I'm going to talk about combustion fundamentals and its applications. So as an aeronautical engineer, we pretty much concentrate a lot on aerodynamics, aircraft structures, avionics like that. And propulsion is one such course which we read much later in the degree, like particularly when you reach your sixth or seventh semester. That's when you start learning about propulsion. So this combustion is probably a chapter or probably a single course or single semester course in our entire degree. but I did my PhD or my entire 5 years course of study in this combustion field. So I'm trying to give you a taste of what combustion is, and if at all you plan to take grad school, probably this is a good option where you expand your horizon on the propulsion branch of aerospace engineering. Um, so I'm going to talk primarily about what is combustion and its background, and try to give you a perspective of its applications, and I'll go a little bit on my PhD work on what I did in combustion. And just let me know if the internet disconnects or if you couldn't hear me uh, through this presentation. So this is our final year project. Dr. Singh was my thesis advisor there, and this is the it was a very amateur project, and that was the time when we were building our propulsion lab in Tagore Engineering College back in 2010. So we started this as a amateur project, but then the way it got developed, we submitted our thesis to the 13th Asian Congress of Fluid Mechanics, and it got accepted. This is the certificate when I presented our research work there back in 2010. So the proud thing about this particular presentation was we were the only undergrad students there in that conference. So with due respect to Dr. Dharmendra Singh Chand, I'm going to go through the presentation. I wanted to uh, tell you all guys, whoever has opportunity to work with Dr. Singh, you are very lucky. So now let me get into the topic for the day. So I'm going to talk briefly on what combustion means. I don't know if you guys have taken a course on this or we are going to about to take their course. But this is going to be a broad overview of what combustion is. Probably I may not be able to cover everything, but I try to put in as much information as possible that I can cover within this 45 minutes duration. So combustion technology, it's primarily emphasized on three basic pillars. One is thermodynamics, another one is fluid mechanics. So as a aeronautical engineer, we pretty much deal with both of these at various stages of our course curriculum. We talk about all the thermodynamics, energy balance, temperature calculation, heat flow, energy flow, all those. And on the fluid mechanics side, we talk about the flows, velocities, pressures, and everything. Um, but chemistry is something which we don't talk a lot, but that is one particular aspect of engineering that this combustion technology emphasizes on. So on the fluid mechanics part, so here I'm going to talk very broadly on each of these topics because I cannot cover all of these in one go, but I'm going to give you a taste of what it is going to be. So before proceeding further, I want to give you a clear definition of what combustion is. Combustion is either a rapid oxidation generating heat. So the combustion process is nothing but oxidizing the fuel. So a fuel can be either a hydrocarbon fuel or a hydrogen fuel or anything based off hydrocarbons, right? So if you take diesel, it's a hydrocarbon, gasoline is a hydrocarbon, kerosene is a hydrocarbon, jet fuel hydrocarbon, or if you have a hydrogen fuel or even biodiesels, they are hydrocarbons. So any fuel is hydrocarbon. So basically combustion is the process of oxidizing those hydrocarbons to generate heat. That is a rapid oxidation. There is another definition for combustion where you do slow oxidation accompanied by little heat and no light. So this is something called a smoldering type of combustion where you slowly oxidize the fuel to generate heat, but it's going to be relatively a little amount of heat. So these are two different ways you can define combustion. But in either case, combustion is basically a chemical reaction that transforms the energy stored in the chemical bonds to heat that can be in a variety of ways. So basically, harness the energy that is stored in the chemical bonds of any fuel um, by oxidizing it. So it's basically the hydrogen and carbon is bonded by the chemical bond. So by breaking the bonds through oxidation, we are harnessing the chemical energy out of it. That's the basic definition of combustion. So I don't want to bore you guys with a lot of equations, but we need to go through this to get an idea of what I'm going to talk in the later part of this presentation. So probably you would have learned in your school or somewhere in your chemistry class about stoichiometry. If you don't hear or if you have never heard about stoichiometry, this is going to be the definition. Stoichiometry of hydrocarbon air combustion. So stoichiometry is nothing but the exact amount of oxidizer that you need to burn a fuel. In this case, the oxidizer is air, but you can write the equation for just oxygen. So this is the stoichiometric equation for a hydrocarbon fuel where X and Y stands for the number of carbon and hydrogen atoms. So O2 plus 3.6 N2 is the chemical composition of air. So when air burnt with a hydrocarbon fuel, it generates the first product of combustion is carbon dioxide, and then water, and then nitrogen, because nitrogen is inert and it's not going to react with anything. So in hydrocarbon air combustion, the primary products are carbon dioxide and water. So AF stoichiometry is nothing but air to fuel ratio stoichiometry. So to burn a given amount of fuel, exactly how much air do you need? That is calculated by using this formula. 4.76 is nothing but the molar based, and then multiply by the molecular weight of air over molecular weight of fuel. So I just put in a example calculation. So when you burn methane, which is the chemical formula is CH4 in air, it basically produces 1 mole of carbon dioxide and 2 mole of hydrogen, and then 7.52 mole of nitrogen. So depending on that, to do the stoichiometric calculation, to burn 1 kilogram of fuel or 1 kilogram of methane, we need to have 17.1 kilogram of air to burn it completely. So that's the definition of stoichiometry. And in the field of combustion, pretty much everyone uses the word called equivalence ratio. So I'm going to define this equivalence ratio here so that we are going to use this term later on in the presentation. So the definition of equivalence ratio is it's the ratio of ratios. You can see there is already a air to fuel ratio, and then it's another ratio here. So it's basically the theoretical air to fuel ratio required to complete combustion over the actual air fuel ratio. So when this is equal to 1, it's basically the equivalence ratio is nothing but stoichiometric ratio. But if this ratio is less than 1, it means fuel lean condition. Where you can see here is when the denominator is higher, it's basically the actual air in the reaction is higher than what it is required for a stoichiometry balance, which means it is a fuel lean combustion, nothing but oxygen rich or air rich combustion. When this ratio is greater than 1, it's a fuel rich combustion or a oxygen lean combustion. So when we say fuel lean combustion, is there any practical application, or what does fuel lean combustion means? um, we can say that diesel engine combustion, where it's primarily a fuel lean combustion. A fuel rich combustion is somewhere where you have more fuel than the oxidizer present in the combustion system. So I'll try to keep this more interesting as possible by not giving more equations, but I'm trying to explain what this concept is. So there is something called flammability limits when you talk about combustion. So whenever there is a combustion of fuel, or whenever there is a fuel that is burning, so there are certain favorable conditions that it requires for it to combust properly. So in this left graph, you can see that the red color is the hydrocarbon. So this is basically the relative percentage of hydrocarbon and air. Hydrocarbon is nothing but fuel. So we can see that uh, every fuel requires a certain ratio of fuel and air in the combustion system for it to sustain a flame. So if suppose the fuel is lower than the required range, then it's going to extinct. It's called a lower flammability limit, which means the the system doesn't have enough fuel for the given amount of air to combust properly. The same way, if the system has too much of fuel and little air beyond the flammability limit, this is called the upper flammability limit of the fuel. So I have given a few examples here where for a diesel fuel, so these percentages are a percentage by volume. So if you have 100 liters of air, between zero point 0.6 liter to 5.5 liter of fuel you can burn in that system. So this is typically where the diesel engine combustion takes place. The same way for the gasoline, between 1% to 7.6% of fuel. For methane, 5.3 to 15%, and for hydrogen, it's a wider range, 4% to 75%. So now, since we know this number, why it is significant and what valuable information that this is giving. So think about it. So if you have, so we know that the entire atmosphere is filled with the air. So as long as you are inside the earth, you are somewhere surrounded with air that consists of 21% of oxygen that is required for burning any fuel. So if this combustion, the advantages of having a lower or a shorter range of flammability limit is storage. So when you store a fuel, we don't want the fuel to burn. Like if I have a diesel tank stored somewhere in my garage, I don't want that to catch fire and burn. So for that fuel not to catch fire, we need to make sure that the the in the diesel tank it shouldn't have more than 5% of air inside the tank, because that's going to be the excuse me that's going to be a combustible mixture present in the tank, and we don't want that to happen. The same way with gasoline, you don't want more than 7% of air present in the tank, within this range, this amount of air present in the tank, because it's going to pose an hazard of having a combustible mixture in the storage tank. But the the with respect to hydrogen, the problem with the hydrogen as a fuel is this is the reason, because it has a really wide range of flammability limit. So anywhere between 4% and 75% of hydrogen in the system, it can catch fire. So hydrogen has a pretty wide flammability limit. So that the in other words, we can say that it's really difficult to store hydrogen in a tank, because we have a higher probability of hydrogen catching fire during storage. So that is one side of flammability limit, flame or wider. So that's the con of having a wider flammability limit. But on the other side, in a combustor, when you want the fuel to burn, hydrogen has a wider flammability limit. So hydrogen is a favorable fuel when you want to operate your combustion system at a wider range of fueling condition, because hydrogen is going to burn pretty much on a wider range, whereas the other three fuels, it has a very narrow range of burning. So you need to be there in that range for that combustion system to burn. So that poses the challenge of burning diesel fuel in a jet engine, where if suppose you are slightly outside this boundary, you will end up with a flame blowout. And as a aerospace engineer, we know that we don't want flame blowout to happen while the engine is in operating at a much higher altitude, or at even at ground condition, we don't want the combustor flame to blow out while it is under operation. So having a pretty good knowledge of flammability limit it's an essential information while you design a combustor system with a particular fuel. So while designing a combustor system, you need to know which fuel it is going to be operated on. Once you know the combustor system and the fuel, having a knowledge of the flammability limit is essential to understand the system and to better design it. So this is another criteria when you think about or when you study combustion. So this is something which my advisor taught me in the grad school, how to represent the whole combustion phenomena into a single mathematical equation. Probably some of you may have seen this equation. This is the classical Arrhenius equation. Probably you would have learned in your chemistry class. But when we learned in this equation in our chemistry class, we would have thought only about the rate of reaction of that equation. But in terms of combustion, we can see that this left hand side is basically determining the rate of reaction. Rate of reaction means the rate of how the flame propagates in a combustion system. It is directly proportional to the molar concentration of the fuel. So how the fuel gets consumed. The more the concentration of the fuel, the higher the rate of the reaction will be. And then this is called frequency factor. This frequency factor is basically collision based on collision energy. Like when you read the definition of temperature, you know that temperature is basically a matter of randomness and the collision energy present in the system. So it's basically this parameter determines that collision in the system, and this is a function of again pressure. With a higher pressure, this number is going to go up. And then ea is the activation energy. So and r is the initial gas constant and t is the temperature, and this is a exponential function. So for initiating a chemical reaction, you need a lot of activation energy because it's on the exponential side. So you need to provide a lot of activation energy and temperature to initiate this reaction, and with a higher fuel concentration and more pressure, you are going to burn the fuel, right? This is the same equation on which our entire firefighting department works. All the fire extinguisher, how we design the fire extinguisher, and how firefighters work. You always hear about all these forest fires and residential fires and everything, right? So this is the basic equation on which our firefighters work to put down the fire. So the reverse side of it is to if we want to extinguish the fire, basically we want this to go to zero, this function to go to zero. For that to happen, we need to minimize all these parameters and try to make that to zero, right? So how to reduce this? So this is basically the fuel concentration. To reduce the fuel concentration, that's when we use carbon dioxide extinguisher, where basically this carbon dioxide, which acts as a dilution, it's going to bring down the molar concentration of the fuel present in that fire environment. So to reduce the collision energy, halogens are inert gases. They are used. So when you pump a halogen gas towards a fire, it basically absorbs the collision energy in the reaction and reduces the probability of reaction progress. So you can either put carbon dioxide to bring down the molar concentration, or put halogen into the flame to bring down the collision frequency. Or we all know if you put water on fire, it's going to extinguish. And how does that happen? It's both by reducing the molar concentration to a certain extent, but primarily by reducing the activation energy and the temperature. When you bring down the temperature of the combustion system, it's basically exponential decline. So even a slightest reduction in temperature, this reaction rate is going to go down a whole lot. And on top of it, when it brings down the activation energy, the entire reaction is going to kill the reaction rate here by putting down the fire. So this is the whole phenomena of how fire extinguisher works. And when I initially learned this equation, that's when I realized how complex this combustion is, and how it depends on all the different parameters that we would have studied. We call it as physiochemical thermal parameters. So it's basically, it involves temperature, it involves fuel chemistry, it involves flow, it involves all the stuff, all the science that you have learned till this point. Like you learn thermodynamics, you learn fluid mechanics, you learn chemistry. So even you learn solid mechanics. The strength of materials is part of porous combustion, where the strength of the material is going to decide how the combustion is. So when you get into combustion, pretty much you use the knowledge that you have gained in every other subject in this phenomena. So this is what amazed me when I started learning about combustion. So I thought I will put that here. So now we will go on different combustion modes and flame times. I think I'm getting really slow here. We need to stop the presentation by 10:45, right?
Yes, sir. 10:45 is the time because
Okay.
students are having lectures, remaining classes from 11 o'clock. So that.
Okay. Okay. Yep. I will try to push it up as much as possible.
Okay, sir. Sure.
Yep. Thank you. So the combustion can occur in two modes. One is flame mode and flameless mode. So we can actually have combustion without a flame. It's called flameless combustion. I'm not going to talk about this in today's talk, but if you guys are interested, you can go on Google flameless combustion. It's basically you burn the fuel without having a flame. So this is not a new technology. This has been around for more than 30 years now, but this is a very cool concept, and I got to see this flameless combustion in an industrial visit here, where I really witnessed this. But today I'm going to talk about just the flame combustion, where there are two types of flame combustion. One is a pre-mixed flame, another one is a non-pre-mixed or diffusion flame. I'm going to talk more detail about these. But before going to that, let's be clear on what is a flame. A flame is nothing but a wave. It's a self-sustaining propagation wave of localized combustion zone at different velocities. So a flame is nothing but a wave which is self-sustaining, which means that it feeds itself to sustain and it propagates at a frequency. So for a flame to live, it has to be localized. So a flame cannot be there everywhere. It has a front and it has a wave front that moves progressively. The flame occupies only a small portion of the combustible mixture, and it cannot be there all through the reaction. It's the flame front is nothing but the wave front. A discrete combustion wave that travels subsonically. So when the combustion occurs subsonically, it's called deflagration. So we call the combustion in different names. Deflagration means when the flame is a self-sustaining but it travels subsonically, less than the speed of sound, then it's called deflagration. When it travels supersonically, it is called detonation. We get to see this in in scramjet combustors and all the high-speed engines where we see the detonations. The fundamental propagation mechanisms are different between these, but just to get an idea, here you can see that I have never talked about the term called explosion, because explosion is not a flame. Deflagration is a flame, detonation is a flame, but explosion is not a flame, because explosion doesn't have a flame front. It is a uncontrolled combustion that occurs spontaneously. That's the reason explosion is not a type of flame, but it's type of combustion. Okay, so now I'm going to talk about the laminar premixed flame, or here I talked about premixed flame, right? So flames can be categorized into two types, premixed and non-premixed. And the non-premixed is also called as diffusion. The same way it can be categorized as laminar and turbulent. This is similar to our fluid mechanics definition of laminar flow and turbulent flow. Similar to laminar flow is the same. It's just the flame where the streamlines does not cross each other, and it does not change with respect to time. Whereas like turbulent flames are complex chaotic flames, and it follows all the definitions of your turbulent flow. So here we are going to talk about a laminar premixed flame. So a laminar premixed, what does premixed stands for? Premixed stands for the fuel and oxidizer is nothing but air or oxygen, uh, mixed at the molecular level prior to the occurrence of the chemical reaction. So before the fuel and oxidizer meet at the combustion flame front, they meet and mix with each other. So when it reaches the combustion flame front, they both are already mixed. So here you can see that from this tube. So this is called a Bunsen burner. I hope you have seen this before. So this is all there in all the chemistry labs, where the premixed fuel. So this is the diagrammatic representation of the Bunsen burner. The premixed fuel and air goes from here, and then this is the premixed flame front, where when when it reaches the flame front, the fuel and air is already mixed here. So With the flame color, we have different types. So we can see, so the flame color suggests a different flame temperatures and at each location. Red is the lowest, and when you see a white region of the flame, that's where the highest temperature is. And this is another laboratory picture where we can see the laminar premixed flame. So in reality, or in actual application, where do we have premixed flame? Think about our gasoline engine or your petrol engine, like in your car or in your scooter or in your motorbike, where you have carburetor or the fuel mixer and everything. That's where that's an example of premix flame, because when it gets injected into your cylinder through your carburetor, the fuel and oxidizer is already been mixed there. So this is one example of premix flame. And here I'm going to talk about the application of flame mode and non-flame auto ignition mode. So in a spark ignition engine, when you have your charge injected, and then when the spark is ignited, it starts a flame, and the flame propagates through the cylinder, pushes the cylinder down, right? This is how you normally combust fuel in a spark ignition engine. But there is a special phenomena called engine knock. So the engine knock is basically a rattling sound that you hear in one or more cylinders. It is because of the premature tendency to ignite, a tendency to ignite prematurely. So before the spark could spark the fuel, because of the high temperature and pressure present in the cylinder, the fuel auto ignite itself. So that's when probably you'd have heard the name called octane number. So the octane number is a branched fuel. So whenever you have a branched fuel, the highly branched compound burns smoothly, so you'll have little knock. A heptane is unbranched, that pretty much deals with uh, knocks badly. So this is basically octane number of 0 and octane number of 100. That's when you go to the gas station or fuel station, you see it, there will be a octane number presented for the fuel. The higher the octane number, the lower will be the knock. So then let's go to the diffusion flame. So this is the classical example of a diffusion flame, the candle flame. So here the reactants, and so the reactants, the fuel and the oxidizer, they both are separate until they meet at the combustion flame front. So in a candle flame, what happens is when you burn the candle, basically the wax gets vaporized when, and that vapor meets with the oxidizer that is present in the air at the combustion flame front. So this is how the diffusion flame occur. Here you can see that in the burner, the fuel alone is coming, and the air comes from the atmosphere, and at the flame front. So these are the different flame fronts of the combustion flame. And here you can see a full range of equivalence ratio throughout the flame. I have defined this equivalence ratio where the equivalence ratio greater than 1 is a fuel rich flame, and equivalence ratio less than 1 is a fuel lean flame. Whereas in a diffusion flame, a equivalence ratio is typically infinite, because on the particular ratio, the denominator is going to be 0 for diffusion flame. So this is the classical diffusion flame example. So this is just for some curiosity. So when you have a diffusion flame on Earth, like a candle flame on Earth, it's pretty much going to look like this. But if you have it on space, it's going to be look like this. It's called a microgravity combustion. Why does this happens? Because of the gravitational force present in the Earth. So because of the gravitational force, the gravity is pulling down the flame here, and then because of the buoyancy effect of the gravitational pull, your flame always tends to go up. This is the reason, even if you hold your candle flat or even pointing towards down, your flame always go point towards up. The reason for that is because of the presence of gravitational force and the gravitational pull. And the buoyancy is basically the occurrence of the gravitational force. Whereas in the space, that doesn't occur. It even though it's still pointing upwards, because there is microgravity present in space, but it won't extend like this. So example of diffusion. So I talked about the pre-mixed flame, on the real-time example for that is a gasoline engine. The same way for a diffusion flame, the classical real-time example is a diesel engine combustion. I hope you all know the difference between spark ignition engine and compression ignition engine. Spark ignition engine, you inject the charge, which is the fuel air mixture, which is then combusted by introducing a spark through the spark plug. Whereas in a diesel engine combustion, you do not have a spark plug because you're going to induce combustion by pressurizing the fuel beyond its auto ignition temperature. So when it reaches the ignition temperature, the fuel will combust by itself because of the compression. That's the reason you have diesel engine have higher compression ratio. So in this case, when the fuel is injected into the cylinder, okay, and then because of compression you have hot air, and the mixing of those occurs here. So this is the classical diffusion flame. And but you know that in the cylinder it is completely filled with air. So as it propagates into the air, it forms different regions of flame into rich combustion and then lean combustion. So these are the different zones present in a diesel flame. So this is the theoretical schematic diagram of how a diesel engine flame looks like. So now let's go back to our Bunsen burner example. Here you can see that this blue line is the blue flame is the premix flame, because you know the fuel and the fuel and air is coming through the tube because it's a premixed, right? And this is the premix flame where the fuel and air is already mixed before entering the combustion zone. Whereas you also see a secondary flame, like you can see there is two flames that are encompassed each other. There is a secondary flame. This is a diffusion flame. The reason for this is when the fuel and air comes through this, part of the fuel get oxidized here, and then because of the velocity, some fuel escapes the premixed flame zone and tries to go to the atmosphere. That's when the air entering from the atmosphere try to burn that fuel, and because of that you will have fuel coming from this end and air coming from this end, and they meet at the combustion flame front, which is the definition of a diffusion flame. So in a Bunsen burner, we actually have both a premixed flame and as well as a diffusion flame. So now let's try to answer a few questions. What determines the shape of this flame? So the answer is the velocity. Actually, I thought of making this as a quiz kind of interactive session, but I don't think I can complete my entire content before that. So I'll rush through this. So the shape of the flame is determined by the velocity profile of the incoming reactant and how much heat lost to the tube. So now there will be another question: under what condition the flame will remain stationary? Because it's a propagating wave, right? So the flame will keep on moving, but in a burner it doesn't. Why is that? Because there will be a equilibrium condition where the flame speed equal the normal component of the unburned gas at each location. I'm going to explain this through a video, but the flame can only on this burner and be sustained if the unburned reactant velocity that is coming through the tube should be balanced by the burning velocity of the flame. If that doesn't occur, then there will be two other conditions, which is called flame blow off versus flashback. So this is a video. Let me pause it here. So when we have a stable flame, it means when the incoming velocity from the burner tube equals the burner velocity, this flame is going to sit on this burner and it's going to burn as long as the fuel is coming or fuel air mixture is coming. Whereas the blow off occurs when the reactant velocity is higher than the burning velocity. So burning velocity is a tangential component that acts like this, whereas the incoming velocity is going to come like this. So when this velocity, when the reactant velocity is higher than the burning velocity, it's to blow off the flame. The flame is going to just go off. Whereas there is another thing called flashback. When the burning velocity is higher than the incoming velocity, the flame is trying to get inside the burner. Now let me play this video and show that. Okay, that was quick. Now we're going to see the slow motion. where you can let's look at the blow off. You can see how the flame goes up, right? The same way, oh, excuse me, the same way when we look at the flashback, the flame goes back. So here, both of these are undesirable condition, because let's talk in application. We don't want blow off to occur anytime during a combustor is in operation. Take it for aircraft engine. We don't want the flame to blow off when the engine is running mid-air, right? The same way in any combustion application, we don't want the flame to go off, because when the flame is go off, the fuel is still going to be injected out, and that's going to create a hazardous condition. The flashback is another condition where we don't want the flame to go back and burn the fuel inside, because the fuel is coming out of the fuel tank, and we don't want the flame to travel back into the fuel tank. That is the reason we choose a fuel that has a favorable flammability limit for that particular application. And to prevent flashback, we have something called flame arrestor. The flame arrestor is nothing but a wire mesh that we put somewhere downstream of the burner, sorry, upstream of the burner. When the flame tries to cross that, it basically quenches the flame. When I say quench, it means that it's going to bring down the temperature of the flame so that the flame can no longer sustain itself. So these are some critical concepts of different types of flame. How to move from? Okay. Now let's get into something called emissions and pollutants. So this is where all the combustion engineers and all the engineers that design the propulsion systems work on, because we need to be emission compliant to get our products approved from all these emission regulation. For India, it is called Bharat stage. So we have different stage of combustion regulation that we need to meet to sell the products. For US, it is called um, FAA regulation or EPA regulation. There is something called a tier 3, tier 4, like that. And for European Union, it's called EU regulation. So for every country, they have their own regulation. For India, it's called Bharat stage. Now we are running on Bharat stage 4, and probably in the news you would have heard about Bharat stage 6 vehicles, stage 5 vehicles. So each of those stages represent a stringent regulations for each of these pollutants. Pretty much the unburned hydrocarbon, nitrogen oxides, carbon monoxide, sulfur oxides, like that. So we have a stringent emission regulation that we need to follow to protect the environment. So my entire PhD work, and even a huge portion of my current job role, I work on nitric oxide pollution. So in my PhD work, I pretty much dedicated my time on understanding how nitric oxide is emitted or being produced in a combustion environment. And in my current role, I develop after treatment catalyst, and also try to calibrate the engine so that it produce a reasonable amount of NOx that we can after treat we can regulate through after treatment systems. So with that background of combustion, I'm going to talk a little bit about my PhD topic. So at the University of Oklahoma Combustion Lab, we do combustion research on biofuel, not only on just diesel and jet fuel combustion. We also did biofuel combustion research, try to find some vegetable-based fuel like canola oil, soybean oil, and then use those biodiesel based on esterification process. It's called bioesterification. So I think since I'm reaching the time limit, I'm going to talk just a little bit of gist of what my research was. So in every engine research work, they pretty much put the fuel in, test the engine, and then measure all the pollutants out. So we developed a system where we don't want to burn a lot of fuel, because in the testing development, developing fuel is very expensive. So we want to use a very little time and little testing, and reduce the number of tests that you make to characterize the combustion. So for that, we developed this combustion system where we pre-vaporize the fuel and inject it through the system to burn a premixed flame. So by doing that, we are by pre-vaporizing the fuel, we are removing the fluid mechanics parameter like atomization and the spray evaporization, so that we can only study the contribution of chemistry to the pollutant formation. So I'm going to just skim through the slides. So this is a diesel fuel flame with under different equivalence ratio, and this is a palm methyl ester flame under different equivalence ratio, where you can see at fuel rich conditions still it is burning blue flame, which is good because it's emitting lesser fuel. And there is something called global emission measurement, where we put the probe to understand the pollutant emissions using this formula, and then a flame radiation measurement to determine how much heat is radiated through flame. So, and this is to understand the temperature and the species, and this is how we this is the mechanism through which nitric oxide forms inside a flame. So I studied this mechanism to understand in different fuel in different condition how each of these reaction occurs. And I developed a, so this is my PhD work where I developed a formula based on carbon, so based on the fuel molecular formula. So based on the number of carbon, nitrogen, halogen and hydrogen present in the fuel, I try to develop a formula where I put a number for each fuel and try to understand this correlation with the emission index. So this is for different degree of unsaturation value, how the flame appears. This is just a visual appearance. And I have a lot of experimental results, which unfortunately I could not present all of them in today's meeting, but this is, I'm just giving a overview of what I did. So so it took me some time to put this slide because I wanted to digest all the information that I had in my 5 years of PhD work into a single equation. So this is one such equation. There are a few more equations like this in my PhD dissertation, but this is going to give you a direct relationship between DOU is nothing but a fuel-based chemistry value, and this Phi equivalence ratio is the combustor operation. So by directly linking the fuel parameter and the combustion parameter, I am predicting the amount of nitric oxide it is going to be produced in the given combustion environment. So this is a empirical formula based on certain condition. So this developed correlation is useful in predicting a nitric oxide emission. So before developing a particular amount of particular diesel fuel and a combustion environment, so basically this value is a limitation based on the emission regulation. So we know this number. So by knowing this number, we can design a combustion system by using this number and engineer a fuel by this number to achieve that emission target. So this is for a particular family of fuel, but I have this equation for biodiesel blends, petroleum fuels and biofuels. So this correlation was found to be a convenient tool for developing fuel. So this research work is primarily based on new fuel development. We call it as engineering the fuel. So we can actually manipulate the fuel to be used in a particular combustion environment and still meeting the emission target. Sorry to skip through all these. This was the abstract of my work, and in conclusion, so this is my conclusion slide. In conclusion, combustion is a economic development. So as you know, all our transportation is based on combustion. In every field, this is the amount of energy. So if in a petroleum field, and about 100% of energy, about 90% of energy is from combustion, either through direct heating or by steam generation. To even doing the steam generation, we need combustion. So this is in the American industry, but pretty much the entire world has similar chart, where in every industry more than 80% of energy consumption is through combustion. And for a developing country like India, these numbers would be even more higher than this. So it's a very high potential, high environment friendly industry. When I say environment friendly, engineers like us who get into this field are the one who develop much more efficient combustion system, still meeting all the environmental pollution uh, regulations. So it's time for question. I know I have jumped through a lot of slides. Let me get into the questions. I think I got some question here.
Yes, sir, you got one question from one of our student.
Yep. So could you please give a brief on current trend, challenges, limitations on aircraft, rocket engine combustion? How far are we in the future to achieve? Uh, so we have on the efficiency side, we have reached quite a bit. Like we have good efficiency as a combustion system, but in terms of combustion, so when I say combustion efficiency, combustion system efficiency, that is different from combustion efficiency. Combustion system efficiency means how much fuel I'm putting in and how much power I'm getting out. That's different from how much chemical bond that I'm breaking from a fuel and how much I convert it into energy. And you wouldn't believe even our current combustion system have a good 80 to 90% efficiency, but a thermal conversion efficiency is still about 40 to 45%. So there is a huge gap of converting the fuel energy into chemical energy. Still there are a lot of system designs, but because of the thermodynamic concept called entropy, because of the entropy in the system, we lose a lot of energy to the environment when we burn a fuel. So there is still a lot of scope for that to improve. And in another perspective, we got into this biofuel combustion. So I worked on a project for Department of Energy in the United States where we worked on bioethanol. So here the ethanol comes from corn, whereas in India we produce ethanol from sugarcane. Here in United States, corn is a pretty good crop. So they try to make ethanol out of corn and burn it in rocket engines and aircraft engines. There is a quite a bit of success there, but still there is a long way to go. There is still a lot of room to grow. I hope that answered your question.
All right. Yeah. Any other student who would like to ask anything regarding the combustion to Dr. Balakrishnan? All right, sir. I guess so. That's it. The query of the student. So another query, sir, we have got
Okay.
right now with from
So
Tarun Bandu.
yep, when we are designing a combustion chamber, how can we decide the right size and area of it? Also, the significance of characteristic length. So that is a question that I need to answer for. I need to take a lecture for 2 hours to answer that question. But yeah, short answer is characteristic length is very important in designing a combustion chamber, because that's going to tell you how much length the fuel has to propagate, or the fuel and basically the flame has to propagate to burn the fuel. If you if you if your characteristic length is lesser than or shorter than the desired length, then your flowing flame is going to come out of the nozzle, right? And it's going to destroy your nozzle, because your nozzle is not supposed to have a flame. If suppose your characteristic length is higher than the desired length, then your flame is going to end somewhere within the combustion chamber, and you are going to lose a lot of temperature and the exhaust energy that you potentially could have expanded through the nozzle to gain more power. So a characteristic length should be optimum. It should not be too low or too high. Both are not desirable. So characteristic length is pretty much important or very important to design a combustion chamber.
All right. So I guess thank you so much, sir. And on behalf of Chandigarh University and the entire teaching fraternity of aerospace engineering here together, and on my own behalf, I extend a very hearty vote of thanks to Dr. Arun Balakrishnan for gracing your important work with us and sharing with us your findings and opinions today. Thank you so much, sir. And also, we are very thankful to Dr. Dharmendra Singh Chand. It is the sole initiative of Dr. Chand today, that due to which we have Dr. Balakrishnan with us. So thank you, Dr. Chand. Thank you so much. Thank you so much for being in today's session. Thank you, sir.
Yep, thank you very much for the opportunity to share my research work, and I really want to thank you and Dr. Chand, because he is very close to me, and he is more than a mentor for me, and I owe all the success that I have in my life to him. So uh, it's my pleasure to fulfill one of his wishes. So
Yes, Dr.
thank
Chand
you.
has also joined in today's meeting with us. Sir, would you like to speak something?
No, no, thank you very much. Thanks a lot, Arun, for
Thank you, sir.
devoting your time, and
Yep.
really, I am very much thankful to you. You readily accepted my invitation. I am really
Yep.
thankful to you. Thanks a lot. Thanks a lot. Thanks.
Thank you, sir.
May God
Thank you.
bless
And
you.
will this I know this got recorded, right?
Yes, yes, yes.
Yep, maybe I would like to get a copy if I can get a link for
Yes,
Yeah,
this.
yes,
sure,
yes.
sure, sir.
Definitely,
It is
definitely. I will
it is
send you.
yeah.
Yep.
It is,
Thank you, and for all